Hello everyone, welcome to this tutorial. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to detect flooded area in the Valencia. As you may know, a few days ago, a horrible flood disaster occurred in the Valencia and large number of people dead or missed in this region. So in this tutorial, I'm going to show you how you can detect the flooded region using Sentinel data. As you can see, there is a poll here. You can see an image created from European Space Agency about Valencia flood disaster. That here you can easily compare the images before flood event and after flood event using Landsat 8 data. This is the flooded area, and you can compare the after and before situation occurred in this area. So now in this tutorial, I'm going to show you how you can compare before and after event using Google Earth Engine platform. So first of all, we need to go to the region of interest, that is Valencia. Go to search places on dataset and type Valencia. Just like that, click on Valencia, Spain. Directly, you will go to this region. In the next step, we must select the areas in which flood occurred. Here, as you can see, this is the main region in which flood cover occurred a few days ago. You can mark it using marking tools or drawing tools available here. Then we need to call satellite data. Let's get started with Sentinel-2 Level 2A product. Go to search places on dataset and type Sentinel-2 data. Two kinds of product available, Level 2A, Level 1C. As I mentioned earlier, Level 2A data already corrected radiometrically and atmospherically, and there are a lot of tutorials about Sentinel data processing on my YouTube channel, and you can find it on YouTube channel titled Google Earth Engine with Emerson Ahari. So import Sentinel-2A into the code as an image collection. Make a new variable, for example, Sentinel-2 for before event equals to bring image collection and assigns to Sentinel-2 before. Make a filter date for the period of time exactly before the event. If you go to the ESA image, if you go to the ESA example, here you can see the flood actually occurred in October 30, and all images before October 30, for example, the before image here is related to October 8. We can compare all images before October 30 and also the after one, as you can see available here. So go to the back to the code and call all the Sentinel-2 data before October 30. For example, here 2024 October, and also starting from the early October to end of October. For example, just a short period of time is enough, because we don't want to do time series analysis. Just we want to make two RGB images highlighting the flooded area. That's it. 2024 October, for example, October 07. So, and then filter your data based on the geometry or region of interest already selected. Make a print from Sentinel-2 before to see how many data available for this region. 4 images available for this period of time, and here we can make a mosaic command to make a mosaic or single image for this region that represent the situation of this area just before a few days before flood disaster. So now using map.add layer, I'm gonna show you an RGB image for this area before the flooded situation. So if you add .mosaic, you will get a mosaic image from all frames covering this area easily. Or you can use statistical variables, statistical operators such as the average or minimum or maximum. But the most standard method is make a mosaic from all images available for this period of time, that every one of them covering a particular area in this region. Then map.add layer allows us to visualize the Sentinel-2 before. So here Sentinel-2 before, and then you can make a band combination for the visualization here. For example, here we will have bands. I'm gonna make a band composite from near infrared, red, and green region of electromagnetic spectrum. So here we will have a false color composite from band number 8 represents near infrared, band number 4 represents the red, and band number 3 represents the green portion of electromagnetic spectrum. So, and next is the layer name is Sentinel-2 before, just like that, and use the false at the end to avoid automatic visualization. Remember to save your code and run it again. After a few moments, you can see Sentinel-2 before as a single layer under layers. So here we can see the mosaic image for this region. If you want to increase the contrast, go to the layer setting and use the 90% of values available to increase the contrast to have a better look on this region. As you can see, there is a small wetland very close to urban areas and also residential areas, and there are a lot of agricultural fields here. Based on the field shapes, easily we can understand that this region was actually a center for agricultural activity, and definitely large number of people were living in this area. Here easily you can see with 10-meter spatial resolution the residential area and also agricultural fields. So, and now we want to make another image for after event or after flood occurred. Just back to your code and make a new variable as Sentinel-2 after. Sentinel-2 after equals the same image collection again, but here we must filter the data based on after flood period. So if you check the European Space Agency image here, you can see the target data is, but this is for land, but this image belongs to Landsat satellite. But at least we know that October 30 is the date in which we can see the flooded area. So back to the code again, and now filter your data, for example, from October 30 to November 1st, 2024, October 30 to, for example, or we can actually set a shorter time to end up from October 30 to October 31, for example. It's totally up to you. But as long as you use low number of images for mosaicing, then you will have actually better visualization for the flooded area. 2024, October 31. So then filter it based on the geometry, get a print to see if there is any image available from Sentinel-2 in this period or not. So, unfortunately, 0 element mentioned. Here we can actually increase the period of time, for example, starting from October 29 and run a code again. Still no images until November 1st. 2 images are available. If you go to the data characteristic, you can see that in the Sentinel data, Sentinel-2 images available for the last day of October. October 31 is a target image. 2 frames passes 2 frames passed from here, and now we can make a mosaic layer from this data actually. So that's mosaic, and again for visualization, map.add-layer allows us to do the visualization easily. Sentinel-2 after, just make a band combination, a false color composite, combination from band number 8 as near infrared, band number 5 as band number 4 it should be as red, and band number 3 as the green band. The layer name will be Sentinel-2 after event. This image belongs to after event, and use the false at the end to avoid automatic visualization. Remember to save your code and run it again. This time you will have 2 images. One of them belongs to pre-event and another one belongs to after event situation in this area. So go to the layer and you can see the after and before. First we will have the the before image with this status, and also in the second image partially is cloudy. If you increase the contrast here, you can see it is highly covered by the clouds, and also we cannot have a very comprehensive view from the region of interest, but at least you can see that how much water bodies actually comes further and came further, and how many areas covered by the water in these images. You can increase the contrast as much as possible here, and now you can easily compare the after and before situation. If you consider to the lake size here, you will see that all the agricultural areas and most of the residential areas near to the lake covered by the water. Here, as you can see, large areas actually covered by the water, and unfortunately most of them not available because of the cloudy situation that we have here. If you back to the Landsat images, you can see that a day earlier, October 30, using Landsat 8 data, larger area or a wider area affected from the flood event. And unfortunately, in the time I'm making this tutorial, Landsat 8 data for this time is not available. Maybe after 1 week and 2 weeks, you can have access to Landsat data, and you can do this comparison between ESA image and your analysis in the Google Earth engine. So as you can see here. So in the next step, but as you know here, as you can see, actually the flood is a dynamic disaster and highly varies from one time to another time, from one day to another day. And it is very important to have access to the cloud-free images to see the actually to to see and detect the main areas covered by the flood or covered by the water easily and without any problem. And most of the time during the flood events, because of the heavy precipitation, we will face with a very wide actually cloud cover extent on optical satellite data that limits our capabilities to get better understanding about the damages or problems occurred after flood. Because as you know, the visible and thermal infrared regions cannot penetrate through the atmosphere through the cloud cover to show and highlight the benefit of cloud to get a better understanding about what is going on in the cloudy region. So that's why we have to shift to Sentinel-1 data as a radar or SAR products that allow us to actually have a better visualization of flooded regions, specifically for the cloudy dates. So back to the code here, and now we can call Sentinel-1 SAR product available, imported into the code as an image collection number 2 is available. Make a new variable. This is Sentinel-1 before event equals to assigns image collection 2 to this variable and filter it based on before event period starting from 2024, October 2024, from early days to mid days, for example, 2024, again October, for example, October 7th, and filter it based on the location, geometry already defined. As long as you are working with the SAR data, as I mentioned in the previous tutorial, it is necessary to use some particular filters that are specifically used for the SAR data. So now we need to add more filters based on transmitter-receiver polarization. Earth engine filter gets least contains. So the least contains, meaning that go through the all image collections that we have. Imagine we want to go through the all image collection images we have under one image collection, and we want to filter the data based on transmitter receiver properties. Here, transmitter receiver polarization. Polarization equals to VV. VV means vertical. The radar actually, or active microwave radiations radiates vertically in this situation and received vertically again. That's why we say VV, vertically send and vertically receive. So it's backscatter receive. So then make another filter, Earth engine filter equal filter. Now we want to use those data in which instrument mode equals to IW interferometric wets. This is a standard format for the GRDH product that we want to use in the Earth engine. In the Earth engine, or even in any other platforms that we want to do flood detection using Sentinel-1 data. So now get a print to see how many Sentinel-1 images available for this period. Only 2 images available. You can see the 2 images here available, and including VERT, VV, and VH. And we prefer to use the same polarization bands because when we have the same polarization, meaning that we have higher radiation, higher energy, and higher information in the image. And most of the time, same polarization bands works better compared to cross polarizations such as VH. H here means the horizontal, meaning that the electromagnetic radiates vertically and its backscatter received horizontally. The direction of electromagnetic is very important. Electromagnetic waves is very important in the microwave data analysis because they have very long wavelengths compared to the smaller wavelengths such as visible and thermal infrared, and their direction and movements may have impact on quality of data we are receiving. That's why we say that VV works better compared to VH here. So now use the select to find the target band here. I'm gonna choose the VV band as the target for the before data. So now make map.add layer for Sentinel-1 before. It has only one band, no need to make a band combination, and leave the visualization empty, and the layer name is Sentinel-1 before, and use the false at the end to avoid automatic visualization. After a few moments, you will have a new layer under the layers. Sentinel-1 before image is available, but unfortunately the images, the before image not covering our region of interest completely, and now we can actually select a longer period of time, to select the whole, to find more images to cover whole of our study area. So back to the code and increase the period of time from, for example, because as you know, the flood occurred in the late of October. For example, here I can increase the period of time from October 1st to October 25 here. So from October 25, and another filter that should be considered belongs to orbit properties pass, because as you know, the SAR images taken in ascending and descending mode, and the image geometry is different when you is different in ascending mode and descending mode. It is better to filter your data based on kind of orbit properties pass before further analysis. Earth engine.filter, another equal filter created here, and the target properties, target property here is orbit properties pass. Properties pass. So for example, I'm gonna call the descending images. Run a code again and make a mosaic layer using .mosaic and run. Or you can use, maybe we have large number of images for a longer period of time. In that case, maybe for one region we have 2 or 3 images. In that case, it is better to get an average. That's the average does mosaic your region of interest and also combine the existing images based on the average value in each pixel. So run a code again, and here Sentinel-1 before is available. This time whole of area covered, and increase the contrast using 90% of values we have. As you can see, whole of the region covered without any issue, and also without any cloud cover impacts. The urban area reflecting with higher values, and also the water bodies showing a higher absorption because, as you know, the microwave radiations or wavelengths highly sensitive to the surface roughness. The residential area has higher roughness, then we have higher reflectance. But in the water bodies, as we have a smooth area, then the amount of reflectance will be lower. For example, all the ships and boats over the water body, you can see highlighting higher backscatter value because actually they have a rough structure compared to the smoothness that we have over the water bodies. So now this actually differences between water body reflectance and rough surface reflectance allows us to detect the water body with a good quality in their SAR data. If you back to the code here, you can make a same image, but this time we want to limit our data specifically for the time in which the drought event, in which the flood event occurred. This image will be Sentinel-1 after, and as we know already, the flood occurred in, for example, 29 or October 30 here. I'm limiting the date to late of October, from October 30 to October 31. And finally, I'm gonna get an average or mosaic because not many images available for only one day. That's better to use the mosaic process. So Sentinel-1 after again created, and now we want to visualize for Sentinel-1 after event. Let's see how it's working. Sentinel-1 after is created. So seems no images available. Let me to make a print Sentinel-1 after. If you run a code here, you can see no bands available. Maybe we have no descending images for this time. So you can skip the descending images and run a code again. Still, we have no images. Let's to increase the period of time from October 29 to October 31. Still no images to November 1st. And now, as you can see, one image is available. If you go to the data properties, only one image is available for this period of time. And if you go to the data characteristic here, you can see this image belongs to October 31, the last day of October. The image is available. You can get rid of the orbit pass filter because there is only one image. The orbit pass can be used in case we have a couple of images and we want to filter the data based on the kind of orbit pass they have. So run a code again. Sentinel-1 after is available. So now you can increase the contrast using 90% of values. Back to the code here and click on apply. As you can see, this image, unlike the optical data, actually prepare a clear view from areas covered by the flood or water bodies, and you can easily compare the after and before using SAR images here. For example, same time increase the contrast in before and after SAR data, and then you can see how many areas or which areas actually covered by the flood. There it is. And also you can actually clip the image based on flooded area and get an export in from Google Earth Engine easily. So go to the drawing tools and make a new geometry layer, a little zoom out, and then using rectangle tools available here, you can make a rectangle that's covering whole of the region, just like that. And then you can click the output based on this region and get an export here. So that clip allows you to clip images based on the rectangle we created, geometry number 2. So for after and before, that clip geometry number 2. Run a code again, save it now, and here Sentinel-2 before is available. Increase the contrast again by 90% of values, and use after image by 90% of values. Here you can see the extent of flooded region and you can easily compare it. So now in the next step, I'm gonna show you how to highlight the flooded area, because a part of low reflectance values belongs to the previous water bodies we had in this region. If you get calculate the differences between before and after, for example, if we calculate the make a subtraction between before and after image, then we can actually highlight the flooded area. So it is mentioned in the previous tutorial. If you check my YouTube channel, you can find a couple of other tutorials about the flood detection using optical and also using optical and radar data. So here a new variable created as flooded area or flood equals to. So here we can calculate a difference between Sentinel between after and before. First, get the before image that subtracts from after image. Sentinel-1 after. Map.add layer here allows us to visualize the output. Map.add layer flood that is clipped based on the region of interest. That is geometry number 2. Leave the visualization empty and the layer name is flood and use the false at the end. Run the code. Here, as you can see, the flood layer is available, but you must increase the contrast by the 90% of values. So, as you can see, the flooded area highlighted with the white color. And now you can download this file from Earth Engine and bring it up into desktop softwares such as QGIS, Snap, or other softwares you are using. To get an export, there is a very simple scenario. A function export.image to drive allows us to get export from all of the results in the Earth Engine. Couple of arguments should be considered for exporting process. The image I'm gonna get export is a flood that is clipped based on the geometry number 2. This is very important. And the description named for the output is flooded image, and then the scale of output, for example here the scale of image is 20 meter, and you can set 20 meter for the output, or you can resample it to a lower spatial resolution such as 30 meter or even higher values. That allows you to resample to a coarser spatial resolution if you don't need too much details for the output. It's totally up to you. So, and the next parameter should be the region of interest, that is geometry number 2. Scale already mentioned, CRS EPSG 4326. This is a single code we use for WGS84 coordinate system that can be used for all around the world, not limited to a particular region. And the next parameter could be a folder you want to save your data in. For example, I'm going to make a folder as test on my Google Drive and save the output there. These are important parameters that everybody actually consider for saving process. And the next one, for mid-resolution satellite data, max pixels shows the highest number of pixels you can have in each frame. For example, the max pixels should be equal to 1E13, the highest number of pixels that you can have for each output. So save your code again, but I didn't already, and run it again. Switch to the task, and here flooded image is available. Click on run, and again on run, and after a few moments you can save your data. The process of saving just started, and once the tab's color turned to the blue, meaning that the output is ready and you can pick it up from the Earth engine. So, and if you want to reduce the speckle impact on output, here as you can see we have some speckle noises in the output. If you want to reduce the speckle impact on output, it is very easy to apply some sort of low pass filtering process. For example, here a new variable created as dspeckle equals to get the flooded data or flood image first and use the focal mean. Here just focal mean including couple of arguments. The first one is the radius. The radius, for example, could be 30. Higher radius actually brings higher smoothness and vice versa. And the kernel type should be square, should have a square structure, and the unit is meters. When we use the focal median with 30 square meters, meaning that the quality of output will be at 30 meter spatial resolution. If I turn it to 100, meaning that the quality of output will be at 100 meter spatial resolution. It's totally up to you which kind of value you use. So here, replace the flood with dspeckle and get rid of the kernel and iteration. Remember to save your code and run it again. Flood image is available, but as you can see, speckle noises reduced. And if I increase the contrast here, you can see the output with the lower noises. And as you can see, we have a high degree of smoothness in our image, but you can reduce it by radius value. If I turn it to, for example, 30, after a few moments, you can see the flood data with a lower degree of smoothness. Just like that. So, and the output is ready, the flooded image. Now you can pick it, you can go to the Google Drive here, through the opening drive directly. You can go to the Google Drive and download your output and bring it up into desktop softwares such as QGIS or Snap software. If you had any problem regarding to this tutorial, you can compare your code with mine, because the code link is available below the video in the description box on my YouTube channel. And if problems still exist, you can reach me out on the comments and share your comments and ask your questions. I will answer you as soon as possible. Thank you for your attention.